This is Engineer Dan Andrew Magkuyaw, and I would be your lecturer for this subject, Math 142-2 Engineering Data Analysis. For this topic, we're going to discuss statistical intervals for single sample. So, why estimate? Engineers tend to do estimation or approximating a certain value, say for example, voltages. Using the data from samples, we can estimate the population parameter of the voltage using statistical tools. For this lesson, we're going to apply statistical methods in the analysis of data. At the end of the lesson, the students are expected to construct confidence interval on the mean of a normal distribution using the normal distribution or the t-distribution method. We're going to construct confidence interval on the variance and the standard deviation of a normal distribution. We're going to construct confidence interval on a population proportion, and lastly, we're going to use general method for constructing an approximate confidence interval on a parameter. Confidence interval on the mean with variance known. So if x bar is the sample mean of a random sample of size n from a normal population with known variance sigma squared, 100 times 1 minus alpha percent confidence interval on mean is given by the formula mu is greater than or equal to x bar minus z of alpha over 2 times sigma divided by square root of n. And for the upper limit, it is less than or equal to x bar plus z of alpha over 2 times sigma over square root of n. So this would be the errors of the distribution. Now, this z of alpha over 2 is the upper 100 times alpha over 2 percentage points of the standard normal distribution. So for the sample size of a specified error on the mean, with variance known, if x bar is used as an estimate of mu, we can be 100 times 1 minus alpha percent confident that the error x bar minus mu will not exceed the specified amount E when the sample size is n equal to z of alpha over 2 times sigma over E quantity squared. So if you want to estimate the sample size, you use the z value times sigma over E quantity squared. And we usually round up this value. We intend to have a whole value for the sample size. So this difference between the population parameter mu and the sample statistic x bar, their difference is the difference in the estimation, which is what we call the error. So this error is z alpha over 2 times sigma over square root of n. So this is the error. And the standard error of the estimate is just sigma over square root of n. So for one-sided confidence bound on the mean with variance known, so if variance is known, we can use the standard normal distribution. So a 100 times 1 minus alpha percent upper confidence bound for mu is given by, so for upper confidence bound, we use mu. So the parameter mu is less than or equal to the upper confidence bound u, which is equal to x bar plus z alpha times sigma over square root of n. While for the lower confidence bound, So a 100 times 1 minus alpha percent lower confidence bound for mu is given by x bar minus z alpha times sigma over square root of n. So this one. This is equal to the lower confidence bound L, which is less than or equal to the mean. Now, for the large sample confidence interval on the mean, if we consider the sample to be large enough, so large, based on our previous discussions, we say that it is large when n is greater than or equal to 40 from the textbook Montgomery. But for other references, when n is greater than 30, we consider it large. So we use x bar minus mu over s divided by square root of n. Hence, it has an approximately standard normal distribution. Thus, for the mu, it would be x bar minus z of alpha over 2 times s over square root of n for the lower limit. And for the upper limit, it would be x bar plus z of alpha over 2 times s over square root of n. This is a large sample confidence interval. Take note that n must be large. For mu, with the confidence level approximately 100 times 1 minus alpha percent. Now, let's have some examples. For a normal population with known variance sigma squared, answer the following questions. What is the confidence level for the interval x bar minus 2.14 sigma over square root of n less than or equal to mu, which is also less than or equal to x bar plus 2.14 sigma over square root of n. So for this problem, you're going to observe that this is negative 2.14. So z lower is negative 2.14, and for z for upper, it is positive 2.14. For letter B, what is the confidence level for the interval from negative 2.49 up to positive 2.49 for the lower and upper values of z respectively? What is the confidence level for the interval negative 1.85 to positive 1.85? Next, what is the confidence level for the interval mu less than or equal to x bar plus 2 sigma over square root of n? So the upper confidence bound is having a z value of 2. Now, for a normal population with known variance, what value of z alpha over 2 in the equation gives 98% confidence, 80% confidence, and 75% confidence? So in order to solve this, we can use our calculator. Now, take note that your calculator must be in statistics mode. And how do we set that? We do mode, stat, and then one variable. So we press all clear, and then after that, shift, stat, and then we want the standard normal distribution. So 5, and then 1. So we are looking for the probability. So for this probability, shift, stat, distribution, 1. So we're looking for the probability that it falls between the two values of z. So P of upper value of z minus the lower value of z. So it would always be upper minus the lower value. So let's try to solve problems, or let's try to solve these problems. So when x bar minus 2.14 sigma over square root of n up to x bar plus 2.14 sigma over square root of n, so the two values of z would be, so for the upper it is 2.14, and for the lower limit, it is negative 2.14. So when we compute that, it would be 0.9676. So just to show the solution, we have from negative 2.14 to positive 2.14, it would be phi of 2.14 minus phi of negative 2.14. So that's 96.76% confidence. For the second one, it's from negative 2.49 up to positive 2.49. So that would be phi of 2.49 minus p of negative 2.49. So that is why we can write it down as phi of 2.49 minus phi of negative 2.49, which is equal to 0.98722 or 98.72%. So observe that if we increase z, we also increase the confidence level. So next one is from negative 1.85 to positive 1.85. So we encode this as 1.85. So always upper minus lower. So upper 1.85 minus negative 1.85. So that's 93.57%. So phi of 2.49 minus phi of negative 2.49, 93.57%. Next, so what's the value to the left of z equal to 2? So that's phi of 2 or 97.725%. So we can type that as p of 2. And that would give us 97.725. Now, if we are given with the confidence level, say for example 98%, and it is said that it is two-sided confidence interval. So we have here 98%. We find the errors, so 98% is the confidence. So outside we have 2% error. This 2% error is divided into two parts, the lower tail and the upper tail. Now, if we're going to look at our statistical table, the value that would give us 0.01 is 2.33. For 80%, it means 20% would be allotted for the error, thus 10% at the lower tail and 10% for the upper tail. Thus, we will be having z value of 1.28. Negative 1.28 for the lower tail and positive 1.28 for the upper tail. For 75% confidence, 25% would be for the error, 12.5% on the lower tail, and 12.5% on the upper tail. This would give us a z value of 1.15. These are the references used in making this video lecture. So this is me again, Engineer Magkuyaw, your professor for Math 142, and I will be summarizing the discussion as engineers and scientists uses a lot of statistical values, mean, standard deviation, variances, proportions, among other values. Now, engineers and scientists tends to approximate or to use all of these values rapidly or urgently that we need to estimate these values. And how do we estimate? We use confidence interval or confidence level or this estimation. So we use the sample data, and from this sample data, we can predict the value of this parameter. So for more example, please watch the succeeding videos. See you for next videos, and thank you for watching.